This is week 11, Thursday. The agenda today, I'm going to do more examples on combined loading. Okay, so we are on Tuesday, we're on this problem. So we found out what is our axial load, PZ, which is minus 100 times 10 to the power 3. We found our shear force in the y direction, which is equal to 25 times 10 to the power 3. And we found our moment about the x-axis, and then a moment about y. So where we stop, okay, is we're analyzing this data, this view, okay, x and z plane. So we know that we have a Vx, right, is equal to twice 8 times 10 to the power 3 Newton. So it's equal to 16 times 10 to the power 3 Newton. Okay. So the formula we're going to use on the element is equal to Vx over Iyy Qy over T, right? So we are looking at element A and element B. Okay, so we want to know the stress state of element A and element B. So now I'm going to put in this view. Okay, so this view over here is a cross-section view. Okay, so we know that we have our Vx. Okay, running at 16 times 10 to the power 3 Newton. So now the major web, okay, we construct our shear flow on our major web. Okay. And then the shear flow can come into here and here. And we know over here, this is our element A. And we know over here, this is our element B. And what we can see from here is that element A, right, is not equal to 0, where element B is equal to 0 in terms of shear. This is because at element so over here, right, it's equal to 0 because it's one of the what? Terminus. Okay. So now we have more or less have everything already, right? So what we're going to do is we are going to determine. We use a new page. We are going to determine the stress state at element A first. Okay, we're going to do the stress state of element A. So let me copy this diagram again. Right. So to see clearly, over here, this is our element A. Okay. So let's determine our normal stress in the Z direction. So if I have to draw transformation, X, Y, and this is Z. So our normal stress will be in the Z direction. And this will be equal to PZ over A, plus or minus. We don't know yet for now. I think we know. We just last week or last lecture we know whether it tends out on compression. But anyway, I'll write the general form of the formula first. So mx over ixx multiplied by y. Again, plus or minus my over I yy multiplied by x. Okay, so we are going to focus on element A. Okay, so we know that pz is going to induce a compression. So minus 100 times 10 to the power 3. And then the area, okay, so the area we can directly get from the table. We know that this question we are dealing with 41.7. Okay, so this information is important to us. So the area is 5320 millimeters squared. Okay, so 53, let me be sure, 5320 times 10 to the power minus 6. Okay, then if we look at moment in x, okay, so moment in x, if I were to look at this view now, is going to generate a moment in terms of x. Okay, so this is our moment in x. Okay, so it's going to be going this way. Sorry, I'm doing a moment about x-axis. So moment about x-axis is doing this. Okay, so we know that moment about x, we know that the value is 22750. So let me recap. Okay, so if we look at last Tuesday notes, right? So this is moment in x, right? So we know that moment in x, if we look at, we look at this view, right? We realize that is in this direction. Okay, so this is the direction that we spoke about. So if I'll go back to our lecture today, I do apologize for, yeah, so it's in the right direction. So the moment in x is going in this direction over here. Right, so this is compression, this is what, tensile. So over here, so we know that it's going to be in tensile plus, right? So moment about z, we know the value is 22750. And then divide by ixx. Okay, so from the table, ixx 40.8. Times 10 to the power minus 6. Then the distance y, okay, so the distance y is this distance over here. So let me get the cross-section view, then we can visualize better. Right, so the y distance is, this is the y distance. So this is where we have our element A. So this is the y distance, right? So it's equal to d divided by 2. Okay, so we go over here, the depth, which is 0.205. Divided by 2. Okay, then we come to moment about y. Okay, so we look at moment about y, right? It's going in the other direction. Okay, so this is our moment about y-axis. Okay, moment about y. So this is compression, and over this side is tensile. So if we draw moment about y, it's going this way, so it's compression. So we know now this is immediately going to be minus, and then our moment about y is 9600 divide by IYY. So you look at the table, IY is 9.03 times 10 to the power minus 6. So the position of A, so we know that this is 75, right? And BF is what? BF is, BF you have to get from here is 166, okay? So this is equal to 0.166 divided by 2, right? And then minus by 0.075. Because the distance is from the centroid, right? Okay. So once we have all this, it's time for us to calculate. So it's equal to 100 power 3, 18.797 times 10 to the power 6 plus 57.154 times 10 to the power 6, and then minus divided by 9.03, 8.505. Okay. So from here, we have our minus 18.797 plus 57.154 minus 8.5. So it's 29 positive 29.852 times 10 to the power 6 Pascal. So what we are trying to do down here is, if I'm going to expand element A, right? So if this is our transformation, X, Z, and this is our Y. When we draw our element, okay, so this is our element A, right? We now know that we have a load in tension, which is equal to 29.852 times 10 to the power 6 Pascal. Okay. So the next thing that we're going to find is we have to determine our shear, right? So this is a shear intersecting plane of the one. So shear XZ, and the other one is shear ZX. Okay. So we also know, right, that stress X is equal to 0. Stress Y is equal to 0. So I'm going to change the color for stress X and stress Y. So this is our stress X, and this is our stress Y. Okay. So we only now know our stress Z. So now we need to find our shear. Okay. We need to identify our shear. So I'm going to do the shear first that we have found based on Vx. Okay, I'm going to look at, let me see, is it Vx? Yeah, Vx. Okay. So now, in fact, I'm going to do both. Bear with me. So now the shear is where things can get complicated. Okay, but it will not be that bad. So now I'm going to take, don't undo. Right. So we know that Vx is equal to, which we have calculated or seen it earlier, 16 times 10 to the power 3. So if we now were to, and this is where our point, our element A is. Okay, so this is where our element A is. Right, and then the shear flow go this way. Right. So now we have to find the shear as noted. We are looking for the shear Z X. Okay. So for this case, we are going to use Vx, and we immediately know that this is Iyy. First moment of area about the y-axis, and then divided by t. Okay. So from the table, we know that Iyy is equal to, so you go to the table, our Iyy is 9.03. Okay, so 9.03 times 10 to the power minus 6 meter to the 4. And we also need to find the thickness, which is for this case is our TF. Okay, so thickness, which is TF. So this will be equal to EF is equal to 11.8 times 10 to the power minus 6 or minus 3. Okay. So next we're going to find the first moment of area, and we know